Hello everybody, I hope you hear me well and you see me well. So for the first time I'm trying a new camera that I've just bought. I hope there will be no issues with that. So I'm not even sure if... so I haven't yet tested it properly. And today we will be solving problems about expected value again. This time second part, a bit harder problems. Problems that you can find, there's a link in the description for sums and expected value part 2 on Codeforces, and there are problems. So I've recommended before to try and solve those problems yourself, because it's then more valuable for you. And still, maybe for an important problem or two, I will give you a minute to think about them. Let me open everything on my laptop so I could see if everything is okay. I don't seem to... Maybe something is wrong with my chat application, because I should here see chat messages from both Twitch and YouTube, and I don't. Okay, I see my own message, so I think everything is okay. Okay, hi Keval, hi Vatsal, and let's start. First, we'll solve a problem that was on the previous part on Thursday or Friday, I think, where we had a task with price of TV, and then price of TV went up every day with some probability by $5 or $10, but this time we will solve it with a bit different version. And for that, let's first cover the theory for that. So we said that the very important theory is the linearity of expectation. That is, the expected value of the sum of two events is the sum of two expected values. So even if two events are not independent, if, for example, you have strength of wind and the amount of rain, still you can add that. You can find the expected value of both, and it's easy. So this is called linearity of expectation. But today we will deal a lot with products, and the same formula but with product. So the expected value of the product of two results is equal to the product of EVs is only true for independent events. And independent events are those that whatever happens with one event doesn't affect the probabilities for the second event. That's hi, I watched previous lecture till probability 4 of contribution to sum, so will I be able to understand this? We'll see, I hope so. So, for example, if you roll a die, a 6-sided die twice, the two results are independent. Or if you roll two dice, or if you toss a coin twice. But for example, the strength of wind and the average amount of rain is not independent, so you could use the sum but not the product. And so since today we will deal with products and also with squares and powers, let's understand that the order of words will be very important. So the expected value of square of something is something else with the square of expected value. So here, if we roll a die, so it's 6-sided, it has results possible 1, 2, 3, 4, 5, 6. The average result, so the expected value of this result is 3.5. So this is average. And the square of expected value, so just square of this number, is 3.5 squared. But it's something else from the expected value of the square of the number of pips that we rolled. because if we say now that our result is not the number of pips but the square of that, so 1 of 1, 4, 9, 16, 25, 36, then the average is just the average of those 6 squares. And if you calculate that, it will not be equal to 3.5 square. So it's something else. The order of words here is matters a lot. So the expected value of square is the average value you will get if you want to know what is the average value of the square of some result. For example, if you either get 1 or 10 with 50% probability, then on average you will get 5.5. But on the square will be either 1 or 100, and the average you will get, the average square you will get is 50.5. Let me do some, so this will be useful. We have still our notes from the previous lesson. And one moment. Okay, I will do some notes in a moment, but we should remember that product is true only for independent events. And now we can solve actually this first problem. The price of a TV is $1,000. Each of the next n days, the price goes up by 1% or 2%. So the final value will be product of some numbers. Let's say that there are 3 days. So the final price is equal to 1,000 times 1 plus, let's say, delta 1 is the ratio by which the price will go up in the first day, times 1 plus delta 2 times 1 plus delta 3. For example, if here it goes up by 1%, we say that it's 1,000 times 1.01 times 1.02. For example, if here it's by 2%, here by 1%, and let's say that third day is again 1%. Okay, so this will be the final price of TV. And we know that if we want to know the expected value of some product, and if those single things are independent from each other, then we can just compute the product of expected values. And here, so it isn't set explicitly in this problem, but well, here it says the probability for each is 50%, and we say that for 2 different days this probability is independent. So if in the first day it goes up by 1%, still on the second day the probability is again 50% for +1 and 50% for +2. So these events are independent from each other. So we can say that the expected value of each of them is something. So here it will be 0.015, because it's either that or that, each with probability 50%. So this is the average ratio by which it goes up. So each of them has expected value this much. So the expected value of final price is equal to n values 1.015, so this power n times 1000. But if we, for example, say that if on the first day, if for example on the first day it's 50% that it goes up by 1%, and 50% that it goes up by 2%, but then on every next day it goes up by the same amount, so keep going on 1%, for example, forever for the n days, then even though we can say that the expected value by which it increases on the 5th day, for example, is still the average of 1.01 and 1.02, then we can't compute the product like this. We could do this only because the events were independent. Okay. And we'll move to the next problem. I just watched... Okay, sorry. The second problem is square of wins, and actually for that we need more theorem. So there is some very nice technique that doesn't have a certain name, so let's call it a technique of ordered pairs, and it's just some observation. So this observation has nothing to do with expected values. So try to focus now, because this is the most important thing today. If some elements, if some set has some number of elements, for example, A, B, C. So this is a set with 3 elements, n is equal to 3. Then the very important observation is that this size square is equal to the number of ordered pairs. And this is for some reason extremely important observation, ordered pairs. So ordered pairs of these elements. So what are possible pairs? Well, we can say, we can note them down. AA, AB, AC, BA, BB, BC, and the same with C. Okay, there are 9 of them, and indeed it's equal to 3 square. And of course, so far we don't see any observation from that, anything we can gain from that. But now, if there are some events, for example, let's say there is a set with 4 numbers, and now we know that for each number it will, I don't know, be removed with some probability or something like that. And we want to know the expected value of n square after the removing, after removing each element with probability 50%. Then it's possible to calculate with some dynamic programming. So one thing is to compute dynamic programming with some prefix, so what number of events we already considered and the number of elements that survived so far. So this is O of n square solution. O of n square, this dynamic programming. But it can be done faster with this observation. How? Well, if this thing is equal to expected value of the number of pairs, and we already know that even if some events are not independent, if we consider the sum of some events, for example, we know that if we roll a die n times, the average result will be n times 3.5. So this is average result from one roll, even if tosses are not independent, because the linearity is always true. So here, similarly, we can find the probability for a pair to exist and sum those things up. Yeah, if you roll a coin, if you toss a coin n times, then the average number of heads is n divided by 2, because it's the probability that in the first try you will get heads, in the second try, and so on, and in the last try. Okay, and here it will be the same thing. So actually what we will do is, for each pair, for example AC, there is some probability that this pair will exist after we remove some elements. So there is some probability of AC, And we say that this expected value of the number of pairs is equal to the sum over all pairs of probability that this pair will exist. So let's say that it's called like A1, A2. So we iterate over pairs A1, A2. And let's see some a bit different interpretation. So maybe a brute force solution that uses that observation. Can we solve the problem where it is either 1% increase or flat $10 increase each day? I think we can, but it's not that easy then. I think those messages disappeared too fast for me. Okay. How to solve it? So, if you mix increasing by some percentage and increasing by some value, then the problem will be more tricky, but I think possible to solve. Generally, if at some moment you get, for example, plus $10, you should count the expected value of this plus $10 at the end. So later, at some moments, you will get, for example, plus 1%, plus 1% at some moments. So there are some more like events, more tosses, more days. And you should count the expected value of this plus 10 at the end. So multiply it by those. And I think with this, you will be able to solve this harder problem. You can think of $10 in terms of percentage and then do the same as earlier. I don't think so, Watson. You don't know what is $10 in terms of percentage. Okay, and hello, a bit late. Hello. Okay, so let's remove that and focus on the pairs thing. So let's get a blank page again. And some brute force solution for this expected value of the number of pairs will be for e from 0 to n minus 1. Let's say that events are numbered from 0 to n minus 1. Now, brackets. Now, for j from 0 to n minus 1. Answer plus probability that both I and j will be in the, will survive. Okay, so this is also O of n square solution that is very easy to implement. So generally, instead of doing dynamic programming to so that for each final number of elements at the end we would know what is the probability that we'll get exactly this number of elements, instead for each ordered pair ij, we know that this pair, if it exists, if it survives, both the elements survive, then the answer will be increased by 1. So actually here we can write times 1. So this uses the contribution technique, because the pair ij with this probability will exist in the remaining elements and it will add 1 to the answer. Okay, so this is a correct approach, but quite slow. And also let's think what is actually this value, this probability. Well, so let's say, let's go back to the problem. Here we say that, so let's move to a problem. You bought n lottery tickets, the ith of them is winning with probability pi. The events are independent, what is very important. Find the expected value of the square of the number of winning tickets. So if I and j are different, then this probability will be just equal to pi times pj. So the probability that both events happen. But what happens, so this is for e different than j. sorry, I different than j, then this probability we use. But what if I is equal to j? What then? So this thing, it means probability that I will survive and j will survive. If I has probability 90%, for example, of surviving, then the probability that the following sentence is true will also be 90%. So the sentence was, I will survive and I will survive. So then we don't do multiplication. We just say that it's pi. For example, let's say why we don't multiply here. If we just wonder what is the probability that the I don't know, we get when we roll a die, 6-sided die, we get a 2. Well, it's 1/6. And what is the probability that we get an even result? Well, it's half, because the result should be 2, 4, or 6. But what is the probability that the result will be 2 and at the same time it will be even? Well, it's still 1/6. We don't multiply these two events. If we like very many times repeat this like random thing, so it was rolling a die, then the probability that both these statements will be true is 1/6. This is probability that 2 will be like the number will be 2 and this number will be even. So here we have, once again, this means probability that I will remain and j will remain. And for I equal to j, it's just pi. Okay, and I said this is very slow solution and we can do it faster. Well, if we just find the sum over pij over all pairs, then we can pre-calculate s as p0 plus p1 plus and so on plus pn minus 1. So we can compute that in linear time. And then this whole inside for loop can be write much easier, because so hold this thing. Let me change the color now. Okay. So this is equivalent to just doing answer plus equal. So everywhere we add pi multiplied by some pj. So in other words, it's pi times p0 plus p1 plus and so on plus pn minus 1. So this is just equal to pi times s, except that here we don't multiply by pi. So when j is equal to I, we don't have pi times pi. So actually here I will write minus pi. And here we have, so this for I equal to j, we have just this element, and I will just add it here, plus pi. So over all I, we find the sum over this expression. And after computing first this s in linear time, we have this in linear time as well. So we got now complexity O of n. And this is a correct solution to this problem. And today we will solve a lot of problems that do something like this. So with time, I hope you understand better what we do. Any questions now? Because this is like a very important thing for the whole topic. shouldn't you add pi n times because I is equal to j n times? Okay, but for fixed I, so if here we have, for example, I equal to 0. Here in this for loop, how many times I is equal to j? Only once, when j is equal to 0. So here when we have some particular value of I, for example, I equal to 0, then here only once this will happen. So only once I add pi. So what you mean is that once this I equal to j happens 1 for equal to 0, sorry, I started writing in under my like video with my face. So once it will happen for I equal to j equal to 0, once for I equal to j equal to 1, and so on. But for every I, only once. It's inner circle, so now got it. Yeah, exactly. And thanks, Anton. Okay, let's try the same with the average number, so the expected value of the cube, so the third power, or maybe even the fourth power. So an empty page for that. And actually, by the way, you can simplify that even more, because if you compute the sum s, then now the whole solution is to iterate over I and sum up these values. But also we have in the process the sum of pi, what can be itself replaced with s. And also here we have something like pi times s minus pi square. So let's do some, let's move that a little bit here. So we have the sum over I of pi. So here we are still solving the square version. Of course, this is a good solution in linear time. Just I'm showing that this can be simplified even more. So we are finding the sum of this. Okay? And now the sum over I of this thing is s. Now, maybe let's first rewrite that a little bit. So we have the sum of this pi plus pi times s minus pi square. And the sum over this is s. The sum over this is also s. So the sum over this times s is s squared. And here we have minus the sum of squares. And usually it can be called like s2. So if s1 was the sum and s2 is the sum of squares, then the formula for the answer is s plus s squared minus s2, where s2 is the sum of squares. So the solution can be just like a couple of lines, very easy lines. And now what about the cube? Well, it's very similar. For cube, we have the same thing, just with four loops. Sorry, with three loops. So we have for I, for j, and for k. And now what we add to the answer? Well, if the indices I, j, k are pairwise different, then we'll add pi times pj times pk. If I is equal to j but it's different from k, then we'll add pi times pk. Because if pi happens, so with this probability this is satisfied, this like event happens, and then automatically j happens because it's equal to I. And similarly, if for example I is equal to k but different than j, then the same thing. And the last possibility is that they are all equal. So then we add just pi. Okay. So this is like hardest part to compute because it's most complicated. And we can say that for fixed I and j, we'll try to simplify the inner for loop, similarly as in the previous version. So we try to simplify this part to be, so right now the complexity is n cubic. And we want to first to decrease this to n squared and then to linear time. So how to quicker compute this? Well, if we have some I and j, let's say for simplicity that I is different than j. So assume I different than j for now. And we want to simplify this inner loop. Then what we do? Well, here we find the sum over this product pk for all k different than ij. So it will be just pi times pj times the sum of everything minus pi minus pj. Why? Because this is the sum of pk over all k different than those two. So this will be equal to the sum of this expression over all k different than the first two indices. And also let's remember that here we don't iterate, for example, for k only larger than j and I. Here, as previously, we have from 0 to n minus 1, because in the technique we count all ordered pairs. Here, all ordered triples. Remember, this comes from the fact that the square of something is equal to the number of pairs. So I said that for elements A, B, C, there are 9 pairs. So it's the same thing here. So iterate over all triples. Okay, we computed that. So this was this part. Now for so this we can skip because we said that I is different than j, and this as well. Okay, but here there are possibilities. For example, I equal to k different than j. Then what we have? Well, we have pi times pj. So for one value of k, this will be true, because it's for k equal to I. And then we have just this pi times pj. And also here the last possibility is that what j is equal to k different than I, and it's symmetric to this one. And okay, and we just removed one dimension from complexity, because we don't, instead of iterating over k, we just add this value to the answer. And then similarly you can use tricks like this, sums like this, to improve this for loop to the constant time, and then you will get linear time in total. And in problems like this, what is helpful is to compute the sum of numbers, but also the sum of square of numbers, and later, if we need bigger powers, then the sum of cubes of values, and maybe so on. So we can here write S1 just to make it the same style, and this will be the sum of first powers, so just the sum of elements. Sometimes even we want to use S0. So this is the sum of 0 of powers, so it's just equal to n. So this is just n, and this is the sum over ai or pi, and this is sum of squares, sum of cubes. And so now if we for all j want to find the sum over this expression, then with, so let's do that with blue. Here we would write that, like, we don't want these complicated brackets, so we would write that this is pi pj s minus pi square pj. So this was from multiplying this expression by pi, and minus this times this, so pi pj square. And so the sum over this is easy to do because now we iterate over j, so just the sum over this element is s, unless we iterate over j different than I. Yeah, so we focus just on I different than j. So this single thing will be pi times s times the sum over pj, and the sum over pj will be s minus pi. So this is sum over pj different than I. And more complicated part is here. Sorry that you don't see it well. So here we have the sum over pi times pj square, and now for the sum of squares we actually need this with this second value, the sum of squares. And then if you want to like improve this this next for loop, you will need the sum of third powers. So it becomes more and more complicated, but it's possible to do. Like kth power you can compute in O of k, I think, or maybe O of k squared. Like these equations will be more and more complicated, but they are solvable. Newton's identities. Let me see what's it called in English. Identities. I don't think we use Newton identities here. So I'm not familiar with this term in English, but I don't see here anything similar to what we do here. We do here something simpler. Okay, so we can solve both these problems in linear time. The expected value of the square of wins and the cube of wins. And from this we'll move to a similar problem, but something that was actually used in some contest. So I remember this problem, I think, from some Petrozavodsk contest, or maybe some different ACM ICPC training. So the problem is called light bulbs. And the statement goes as follows. There are n light bulbs and m switches. So initially black color again. Initially all light bulbs are off, and here let's say there are 4 of them, and there are m switches, and both constraints for n and m is up to 50. So these are light bulbs, and now there are m switches, and for every switch we know whether it flips the state of a light bulb or not. For example, 0, 0, 1, 0 would mean that this switch only changes a state of this light bulb. So let's say that these are bulbs. Okay, and for example, if we have something like this here, it means this switch flips the state of first, third and fourth bulb, and then something here. So these are m switches, and we say that initially all bulbs are off, then we click every switch with probability 50%. So if it's clicked, then it changes status of corresponding bulbs from off to on, from on to off, and we want to find the expected value of the number of bulbs that are on at the end, not square, cubic. And this is something very hard to do without this whole technique. So how to do it? I will give you a minute to think about it, because it's important to try to understand from the previous problem this one. So what we do here, what complexity we will get, because here we don't just have probabilities in the input. We have some information, what switch flips what. Okay, so here we know that the expected value of this is equal to the expected value of the number of ordered triples of bulbs that are on at the end. No, here without. Okay. So we just want to find this. So for every triple of bulbs, we want to know the probability that they will be on at the end. So we iterate over every triple. And for example, let's say that we have this bulb, and this bulb. So since we iterate over triples, we already have of n power 3 in complexity, and it will be times something. And what we do now? Well, what we can do is do dynamic programming with 8 possible states. So first we know, so this will be probability that the bulbs are in this exact state. So first we say that dp of 0, 0, 0 is equal to 1. The probability that all bulbs are off initially. And then for every switch, we know that with probability 50%, well, it could be just given probability in the input for every switch, different probability. We update the probabilities in dynamic programming, because, for example, here, if this switch flips the state of this bulb, then we know that from dp of ABC, so each ABC is just a bit 0 or 1, saying whether this bulb is on or off. So from this, with 50% probability, we would move, in this case, in case of these 3 bulbs, to dp of A, B XOR 1, and C. Because if it's clicked, then the state of the second of the 3 bulbs changes. And with probability 50%, it will stay at ABC. And that's it. So we have 8 possible states here, and we'll do the update, and we'll do that for every switch. So we have this times 8, what is a constant, we can skip that, and times m, because for every next switch we'll do this update in time of 8. So we just solved the problem in this complexity. Well, we didn't care here about the implementation details, while in fact it will be a bit hard because sometimes these three indices, so this I, j, k, then some of them can be equal to each other, or they can all be equal. And then something here might change a little bit. I'm not sure about it. I don't see now what would change, but we must be careful for sure in the implementation. Also, when we compute that, we do that to, at the end, after considering every switch, so we considered all of them, so then at the end we know at dp of 1, 1, 1, we have probability that after we consider all switches, all three bulbs will be on. So we add that to the answer. Answer plus equal dp of 1, 1, 1. And then we go to the next triple of indices. We again create new dynamic programming of size 8. We initialize 0, 0, 0 to be 1. This is probability. And we consider M switches. So the implementation actually will be very easy. Sum over subsets. I don't see sum over subsets here. I don't understand what you're saying. So we covered sum over subsets on the previous lecture, but here we don't have subsets. Well, we have something of size 3, but it's easier to think about them as triples. Okay. And the remaining problems are harder. Also, in comments, someone posted some similar problems. For example, on CodeChef there was chef cats tree that you can read later, and indeed it's for the same technique, but it's harder because it has some extra stuff with paths, so it requires more knowledge. So let's focus on problems that I gave here. And the next problem appeared already in the previous stream, but I haven't covered it, I think. So we'll move to that now. The problem is sum length. And given a sequence of length n, find the sum over sum times len power 3 over all intervals. Print the answer modulo billion plus 7. And there is more than one solution. Okay. So for example, if we have 2, 5, 4, then for every interval we add up sum, so we find the sum over sum of numbers times length power 3. So here the sum would be 7 times length is 2, so 8. Okay, for, I don't know, this interval we would get sum equal to 2, 5 and 4, it's 11 times length cubic. So we want to sum that over all possible intervals, also those with length 1. And there are quite a few approaches. One of them, I think the easiest one, is to just use the contribution technique that we used in the previous stream, that we covered in the previous stream, where for every number we want to know in how much it contributes to the answer. So here actually we can say that this sum is equal to this sum is equal to a, for example, ai plus something plus aj. So this is sum over sum interval. So it means each of those elements adds L cubic to the answer. So actually for every element here, we can iterate over all intervals that contain this element, and to the answer add this ai value times L cubic. So we can iterate over I, or instead of I, it will be better to name it B. So this index. Let's iterate over B from 0 to n minus 1. And now iterate over intervals that contain this element. Well, so the beginning of interval must be smaller than B or equal. So let's name it A. So this is beginning of interval. And the end of interval must be after B or equal to. So this represents situation. So this is a sequence. This is some B. And we have some interval with first element A and last element C. So for every B, we iterate over intervals that contain B, and to the answer, we add value at B. So let's call it X for a moment. Let's say that here at this place, the value is X, times length cubic. So C minus A plus 1, I think, cubic. So this is a correct solution in O of n cubic, what is quite slow. Actually, it's very slow because it's much easier to do some brute force in n square without any observations at all. But we will be able to improve that because for this B, when we iterate over where the beginning of interval will be, we actually kind of iterate over how long this interval will be to the left. So if there are, how many elements there are here? 1, 2, 3, 4, 5, 6. So here we have B equal to 6, for example. 6. Then either the beginning of interval will be here, or here, or here, and so on. There are 6 possibilities. And from them you have some values of cubic. So actually we can also say that we iterate. So we try to change this part. So we can, similar to the previous problems, it's okay to have this one for loop to get linear time, but we must make these inside loops faster. And in other words, with some different functions, we can write this down as for, let's say, how to call it? Let's say that L will be length to the left. So L actually will be B minus I think, maybe plus 1. So the length of this part. So from L equal to 1 to B, or maybe B plus 1, I don't like. Let's not care about plus minus 1 because it's something that you should care about in implementation. It doesn't matter for me when I just show a solution. For also the right part, from let's say 1 to n minus B, to the answer we add X times L plus R cubic. And this can be computed quite easily with some maths. How to compute it? Well, if you fix L already, then for R you have what you have, the sum over some consecutive third powers. So this is one way. I think what we should do here is let's create a new blank page. Okay, this state not removed. So Now we want to find the sum over L plus R cubic. Sum from, let's just say we want to find the sum from A equal to 1 to some big A, sum over B equal to 1 to some big B, of A plus B cubic. And this is something not related to the expected values. So it's just some math. Sorry, not big A plus big B, A plus B. So this is something that could be on a contest. How to do it? Well, we can say that this is those two sums of what? Well, it's A cubic plus 3A square B plus 3AB square plus B cubic. So there is formula for that. So this is equal to this. And now we can say that, so we can find each of these sums separately, well, just like with expected values. So we have the sum from A equal to 1 to A, B of A cubic. So this is just B times, we repeat something, so it's just B times the sum. And so we already know how to compute this part because we transform it to B times the sum, and either we can pre-process the sum of cubes up to some n given in the input, or we can use a formula for that. So there is a formula, I can find that in the internet. A bit harder is this part. So the sum of 3A square B is equal to 3 times, so what, for every A we have the sum of B from 1 to big B, so it will be the sum over A square times the sum of B is, so the sum of B from 1 to big B is equal to, I think, B times B plus 1 divided by 2. And also this sum can be either pre-processed or there is a formula for that you can also find. That is, so during a contest I would just Google sum of squares, sum of n squares, something like this, and you'll get a formula. N times n plus 1 times 2n plus 1 divided by 6, and you put that in your code, or you just pre-compute that. You pre-compute the sum up to n, and up to n minus 1, n minus 2, and so on, and you keep that in linear memory. Just one warning, like one note here, is that you must be careful here when you compute something modulo. So just remember about it. If you compute the answer modulo on so billion 7, then remember that the product of three numbers can overflow. So you must take product of 2, then do modulo, then multiply by the third value. Okay, so we are able to find this sum. Of course, it takes some time to do some computations. But now we can do this part in constant time after some preprocessing. So this was one of possible solutions, but not the only one. Let's move to some different solution. Different solution being so if we are interested in the expected value of the sum, well, we want to find the sum of sum times len cubic. So instead of for each element finding its contribution to the answer, we can do something not similar to the technique, instead something more maybe standard. For every length, and up to len equal to n, find this sum over sums of intervals. So let's say that sum of I means the sum of interval, len of I means the sum of interval. Okay, so for example, for len equal to 2, we want to find the sum of all intervals such that their length is 2. And then if you know that this sum is, for example, 7, then you add it to the answer multiplied by len cubic, and here you know len. So you can see here some similarities to previous problems where, so this corresponds to, for every possible result, finding the probability that we will get this result. So instead of looking at contribution, we can, for every len, compute the probability, or here the sum of intervals with this length. And if you have a sequence of numbers, then the sum of intervals with length 3 will have this number once, this number twice, 3 times, 3 times, 3 times, 3 times, 2, 1. So what it means is that this element, for example, is in 3 intervals of size 3. Okay, and if you know the sum of those elements, so this first element plus second times 2, third times 3, and so on, and you know this value for len equal to 3, you computed some x, so this sum. Then if you want to move to len equal to 4, so now these coefficients, how many times each element will appear in some interval, will be almost the same. So this new x for len equal to 4 will be just different by these two values. So you can actually, after maybe some prefix sums, update the value from value in constant time. So for len equal to 1, this sum is just the sum of numbers in the input. Then every new sum is easy to find, and you just print the sum over len cubic times this x you found. Okay, so this was a second approach, and the third one is the hardest, but so you can think about it in home, but it uses what we use today with powers actually. So we have some elements and we have some interval, and we know that to the answer we add, for every element here, for every some ai, we add this number times length cubic. So this is equal to the number of triples of indices here, for example such a triple, or maybe some of them are equal. So for every such triple and element here, we add to the answer ai. But also we want to do it for every interval, so actually I would add one more thing to iterate over that represents the beginning of interval and the end of interval. So 2 extra indices, and those remaining 3 must be between them. They can be over exactly at the same space, just we can't allow such an index be on the left from the beginning. And that might look a bit crazy, but here also a correct solution, but so far too slow, is to iterate over top tuples of size 5 of indices, and also third one more index with to take value from that, and then we add ai to the answer. And here it looks quite hard when you think about it this way, but also from that you get that for AI, its contribution to the answer, so for how many sets interval plus the 3 indices here, so let's remove this, interval plus 3 indices inside, for how many sets like this, AI is somewhere inside. And you can think about it this way. AI must be to the right from the beginning and to the left from the start of interval. And you can think about it as choosing these 5 indices, such that first is to the left from AI and last is to the right from AI. And you can just say that, okay, to the left from AI, here there must be at least 1. So, for example, if there is exactly 1, then possibilities for that, there are something like, let's say, I minus 1, possibility to just put this beginning of interval here. Now here there is something like n minus I plus minus 1, doesn't matter. So this times, here you want to put 4 indices. Actually also it can be exactly here. So it will be something like a minus I choose 4, or maybe power 4. It's a bit hard to here compute because you allow different indices to be at the same position. So actually I think the formula for that, if at n places you want to put like k elements, choose k elements, and some of them can be equal, then actually the formula for this looks like this. And so here I think the formula will be this plus 3. So this is the number of ways such that only 1 element is to the left, and for that you add this I minus 1 choose 2, actually plus 1, times n minus I plus 2 choose 3, plus the same for choosing 3 elements to the left, and so on. And I understand this is quite hard, but it's also a possible approach that you can try to just practice the technique. Okay? One moment. So, we move to 2 hardest problems now. That are just something that both of them I saw in contests. Actually, the second one is created by me. And both of them are very hard if you don't know the technique that we described and we talk about, and are possible to solve if you know that. So, first problem, small power of subtree. You're given a tree of size n up to 100,000, and an integer k, small integer k up to 10. Find the sum over size power k over all subtrees, that is, connected subgraphs. So, let's say that k is equal to, I don't know, 5. Then, if you are given a tree like this, then one of possible subtrees, in the sense that it's connected subgraph, is, for example, this. So this is one of many subtrees, and its size is 3 because it has 3 vertices, and to the answer we add 3 power 5. And some approach for this is to try to, for every possible size of subtree, compute how many subtrees have this size. And it's very hard to do. We'll actually do it easier, because we know that size power k is equal to the number of, so previously we had ordered pairs of or ordered triples. Here we'll have ordered sequences of size k. For example, if there are elements A, B, C, and you want to compute like this size, so 3 power 5, then this number, so 3 power 5, is equal to the number of sequences of length 5, consisting of elements A, B, C. Like trivially, it's 3 power 5. So here we can change a problem from find the size over size power k to find the number of ways to choose a subtree, so connected subgraph, and choose k indices inside this subtree, because each such sequence of k indices contributes 1 towards the answer, because we saw that this size power k can be treated as the number of sequences. So we got slightly changed problem, and this version can be solved like in not so hard way. I think that, just for your information, the next problem will be likely a bit easier in terms of all the different things that you have to know. And here, to solve this small pair of subtree, you need some experience with dynamic programming on tree, because what we'll do is, so this is a tree and this is some subtree for which we already computed everything we want to know for this subtree, and now we do dynamic programming from bottom up. So we already computed something for subtrees, and now we want to combine it in their parent. So what we want to know for such a new vertex, and here a smaller subtree that we computed already, we want to know what is the number of ways to choose some subgraph here and choose some number of vertices, like some I from 0 to k. So what is the number of ways for that? It isn't enough to just say what is the number of subgraphs here, because it isn't enough for us. We want to also, in this subgraph, depending on how big it is, we want to add more towards the answer. So it isn't just about the number of subgraphs. It's the number of ways to choose a subgraph and also choose some vertices there. So for this, let's say that this is some index v and this is u. So for v, for vertex v, we knew the number of ways to here choose a subgraph and some number I of vertices, maybe pairwise equal, just like all the time in previous problems. And from this we can move to dp. So we can move to dp of u of I, or dp of u I plus 1. So this plus 1 would mean that we also add vertex u, but we said that the same vertex can be taken many times. So actually not only we can use move to I plus 1, but also to I plus 2 and so on. So here it can be to I plus 1, I plus 2 and so on, up to k. And how many ways are there to go from here choosing I vertices to choosing I plus 2 here? Well, not only we say that we take this vertex twice, but also it matters in the order of sequence. So this is some combinatorics. If you already chose some three vertices here, let's say ABC, some ABC here, and now you want to put a new vertex u, in one of the places between. So we count ordered sequence all the time today. We count ordered pairs, ordered triples, ordered sequence. There are 4 ways for that. And generally, if here there are I elements and you want to put j new elements, so this is some j, then the number of ways to do that is something like I plus j choose j. Once again, plus minus 1. So I don't want to care about details like this. But this is the number of ways to put j new elements somewhere between I already existing elements. And then we know the number of ways to, in the whole like new subtree here, to choose some subgraph and choose some number of vertices. And also we must be able to merge 2 subtrees. So we have some subtree. So we already moved from subtree to also its parent u. And now we want to add a new child for u. Then we just iterate over the number of elements that we already chose here and the number of elements that we chose here. So we iterate over I from here and j from here. And also we combine them with something like I plus j choose j ways. And we do that from bottom to up. And at the end, dp of root k will be our answer. So this is quite hard problem. So this was in some ACM ICPC training, maybe also in Petrozavodsk, and it was something solved only by a few teams. So don't worry if you don't get all of that. Just try to later get back to this part of the video, and if you have questions, some doubts, just ask me on priv, on, I don't know, Facebook or Discord. Do you have any questions now? So for sure I must modify this chat for later. I think something changed because previously I here saw oh, okay. So here I see what you see. So messages disappearing after 10 seconds, and here I see all the history. Okay. Sorry, I'm new. The one you just circles is not a subtree, right? So are you computing subgraph or subtrees? Yeah, I said the definition here is that it's connected subgraph. Sometimes so of course usually if you have a tree, subtree just some vertex plus everything below this vertex, but here we count something for connected subgraphs. This was called with quotes subtrees in the statement. So like, sorry, I agree that it's a bit confusing. Also sorry that I didn't answer immediately, just I didn't see chat. Okay, so if there are no questions about this problem, we'll move to the next one. So I moved quite quickly today through problems, and we are only with one problem left, so we will finish in like 20 minutes. So if you have any questions about things so far, don't hesitate to ask. And yeah, later, if you want to solve some extra problems, then just read comments here. Also for the first part, for the first block, if those problems aren't enough for you, the like 18 provided problems, then just go through the comments here. You will learn a lot of stuff here. Okay, let's get back to our second part. I love you, sir. Thanks for your videos. I'm very glad people like my videos, so this is why I do it. If it's useful for someone, awesome. Also, a bad thing that I must tell you is that for the next like more than 2 weeks, I I will not do any streams because I'm going to USA for some contests, mainly for Facebook Hacker Cup and Top Coder Open. So I will not be streaming at all. I will try to create some short videos with, for example, a single problem, some like 5, maybe 15-minute videos, and I will upload them to YouTube. Also, using this like break, let's say commercial break, please consider subscribing to my channel if you haven't already. If you want like get notifications about video streams. Also, it helps me because when my channel is bigger, more new people will see it, so it's awesome. And I'm very glad that we already have like more than 800 subscribers, so it's awesome. Thanks. What do you think about the next lecture? So there will be no lectures for more than 2 weeks because I will not stream. One possible topic that I think about is some other technique. So as you can see, often what is useful is not really an algorithm, like for example flow, but instead I would say technique, some way to solve a problem. And also such a way is when you have some, I don't know, items and you must sort them in some order, optimal order. For example, you have boxes that each box has some weight and each has some like durability, how strong it is, and you must put them one above the other, and you must sort them in good order. So strong boxes should be at the bottom, and if something is very weak, it should be at the top, unless it has big weight, so it's very heavy, and things like that have some general technique, and I think about it. All the best for upcoming contest. Congrats on winning 2nd rank in CodeGem. Thank you, John. Sorry, Johan. Yeah. And also I'm considering in Facebook creating some very short videos with some simple problems, for example, like 1-minute solution. So some short, nice problems from, for example, easy problems in Codeforces contest can be explained in 1 minute actually. Just say, in problems like this, do that. And I think like 1 minute videos like that can be like very easy to consume for you, and at the same time they can teach you a lot. So I think about that, but sadly no streams for the next 2 weeks. So I will be back in like 17th of November. Okay, let's get back to problems. Also here we have bonus powers technique. So let's talk about that before solving problem 7. Also I realized, sorry for that. So you can see in at the very top of the screen, you can see here like name, something like a timestamp that says what problem we are currently solving, and I completely forgot about it today. I must like take notes of stuff that I must remember about when I stream. So in the previous stream it was so that later it would be easier to find moments when some problems was being solved. That's fine. 17th I have my semester examinations. Well, awesome, because after examinations you will be able to watch a new stream. So for a moment let's talk about the powers technique. So in the under the block with the first part, someone mentioned a problem about, okay, so actually it was a bonus problem for my problems in the first part, and it was given a tree with big size. So we are given some tree. Find the sum of all paths, length square. So for example, this path of length 1, 2, 3, 4 would contribute 16 towards the answer. And if you want to solve it with something like contribution technique, it's quite hard, unless you use what we already used today, that is sum of numbers, sum of squares, and then in harder problems, sums of cubics of elements. And for a moment forget about the problem, and let's see what this technique is about. If you want to maintain the sum of cave powers, it might help to also maintain the sum of smaller powers. And it will be used in this problem. So we already covered how to find the sum over paths, but it's harder to do for paths squared. So let's say that we have some elements, some A1, A2, and so on, up to AN. And we know the sum of the elements, we know the sum of squares. And we now want to cover a query, an update, that is increase every element by x. So each of n elements will increase by x. And we want to quickly, in constant time, update the values S1, S2. Actually, let's say that the statement only tells us to compute new S2 in constant time, but for that you will need S1. And let's see what happens. So we know the sum of squares, it's S2, but now the sum of squares will be A1 plus x squared plus A2 plus x squared plus and so on. So this will be equal to A1 squared plus 2 times A1 times x plus x squared. So this expression is the same as A1 plus x squared, and plus the same for A2 and so on. And the sum over these elements, A1 squared, A2 squared, and so on, is equal to old S2. So we already know this value. The sum of x squared that will be there n times is equal to n times s squared. And the sum of 2x times a1, a2, and so on is equal to 2x times sum of elements. So S2 will be changed to S2 plus 2x S1 plus x squared times, actually n is the same as S0. So if you want to quickly update Sk, you need to also maintain smaller powers. For example, if you want to know a new sum of cubics, you need to maintain the sum of squares and first powers as well. And then you can do everything in constant time per update. Finally, I'm watching it live today. Happy that you read all suggestions. All the best for your upcoming contest. Thank you, and welcome to the stream. So, this is idea for technique, and let's see that being used in this problem. So here, the only reasonable thing in such a problem is to do bottom-up dynamic programming. So you should often think about that in problems on trees where you want to find the sum over some paths. So for a subtree, change color to red again. For a subtree, if you know the sum of squares of all the paths that start at the root of this subtree and go somewhere down. So if you know this S2, you can, with this technique, update it quickly when you want to extend subtree by an extra vertex. So this is what you must do when you go up. So with this with something like this, if you also maintain the sum of paths and the number of paths, so S0, you can update that. And then when you, let's say that you have here some subtree, and you want to see what is the sum of lengths of paths that go through this vertex. So something like this. So paths like this you want to consider. Well, if length here is L and length here is R, then the square of total length is L square plus 2LR plus R squared. Okay? And you already know L square, like you know the sum over L square, you know the sum over R square, and here if you know the sum over L and you know the sum over R, so the sum of this is like S1 from left 3, the sum over R is S1 from right 3, and you just multiply S1 from left and Si1 plus from right, and with this you get the sum of squares of lengths of all paths that go through this point and go to this subtree and this subtree. So this is how you combine two subtrees in every vertex. And then you can do the same. So if you combine these two subtrees and then you merge them, imagine a new bigger subtree, then you can also add a third subtree in the same way. Just then, like this is generally how you do dynamic programming with like merging subtrees. Then you know something for this subtree, and you merge them with this in constant time. So yeah, that's about this technique. And sometimes we need to first do bottom up and then top down, but I don't think it's necessary in this problem. I think what I described is enough. Okay, so this was a bonus, not really related to the rest of the lecture, but somehow related. Well, it's all about sums, and this expected value thing and summing over like powers is very similar, as you can see many times. Many of those problems can be done in the same way. And the last problem is a problem from my TopCoder round. It's called double life. And let's go through quite long statement, and then I will give you a moment to think about it. So the statement was that you have an army in computer game. The army consists of B bears and H soldiers, humans. So B bears and H humans, both values up to 2000. A bear has 2 hit points and a human has 1 hit point. The enemy archer has T arrows, and every next arrow hits one random alive soldier in your army, taking 1 hit point and possibly killing that person. So let me do a drawing. So you have an army with some number of humans and some number of bears. So this is a beautiful bear, another beautiful bear, and yet another beautiful bear. And every human has 1 health point, every bear has 2 health points. So let's a heart denote a health point, so bears have 2 each. And last bear. Okay, so there is some number of enemy arrows. Okay, for example, let's say T equal to 3, and every arrow hits 1 random soldier, so no matter their health. For example, with probability 20%, it will hit this bear, and then one of its health point will be gone, but it will still be alive. And still there will be 20% to hit him in the next round. For example, maybe in the next round, with probability 20%, this person will be hit and then he's dead, because it was his last health point. And then every person will be hit with probability 25% now, because there are four alive soldiers, and each has equal probability to be hit. So the fact that this person died affected the probability for others to be hit. And now with 25 probability, this bear is dead, because it's hit again. So now we had 20% times 20% times 25% for this situation. And at the end we say that the strength of army is the number of bears times the number of humans times the number of all soldiers, but only we count those alive. So here it would be bears, so we have 2 bears times 1 human times the number of all soldiers, 3. So with probability 1/5 times 1/5 times 1/4, we have this strength of 6. And the fact whether some bears are wounded doesn't matter at the end. If, for example, with probability 20%, 20%, 20%, the bears were hit each once in this order, for example, then the final strength is the number of bears, 3, times the number of humans, 2, times the number of all soldiers alive. Then it would be what? 30. Okay, and the question is about the expected value of the strength of your army after the enemy archer uses all his arrows. And here the statement doesn't have any powers, so usually you can use this ordered pairs technique if it's about the expected value of the number of the square of some size, or third power, or some. In the previous problem we had cave power for k up to 10, and here we don't have power, but it didn't matter that much whether it's power. What mattered was that it's some product of things that are dependent from each other, because if something is independent, for example here, if the fact whether some bear is alive and some human is alive, if that is independent from each other, if for example we say that every person dies with probability 50% and that's it, there are no arrows, no T arrows, then problem is easier because we'll just multiply some expected values. Here it's harder, and if there is a product, for example square, if there is a product of not independent events, so dependent events, then we use this technique. And this is what happens here. So it's not really about small powers, it's about products. Okay, so here, since the formula for strength is b times so bears, humans, and all. In other words, is b times h times b plus h. So b square h plus bh square. Changing this to this expression isn't necessary. I think we can solve this equally easy. It doesn't matter much, but just a thing for you to notice is that, well, we have some powers here. So there is some similarity to problems about squares. But just as previously we have, for example, some size power 3, and then we said that we iterate over triples of indices, some I, j, k. It was because size power 3 is in fact size times size times size, and this product is equal to the number of ways to choose one of size elements from here, one of size elements from here, and the same here. And if we have b times h times all, we can imagine here b elements, so bears, here h elements, here this plus this, and this product is the number of ways to choose one bear, one human, and also one anybody. And this anybody can be equal to bear or human, it doesn't matter. So in this situation, the product bears times humans times all is equal to the number of ways to first choose a human, then choose a bear, then choose some anybody. It doesn't matter if it will be equal to one of those like chosen humans or bears. It's the same thing as in previous problems. Okay, so what about, let's start going towards some solution. Exams are coming, good luck. Okay, some solution. What dynamic programming we can do? Because we will do dynamic programming. If you see constraints up to 2000 and you see some number of one type, some number of second type, it makes sense to do dp of bears humans. This should be your first idea. It's wrong. It will not give us a solution, but it has a lot of sense to have this idea at first, because this is how often you solve problems. So what is wrong with this approach? One thing is that the complexity would be too big, maybe. I think we would get n cubic. Maybe it would be possible to improve a little bit. But the main thing is that if we start with some number of bears and some number of humans, and we have next arrow, then we know that, so instead of bears and humans, let's say that it's big B and big H. Okay? And let's say that we are okay with complexity n power 3. So here n denotes, let's say, the total size of the army, so B plus H. So it will be 4000. It would be too slow, but I'm claiming that even this will not work. Why? Well, we have, what is the probability that now a human will be hit? Well, it's H divided by B plus H. Because we have B plus H people alive, soldiers alive, and H of them are humans. So that with this probability we will go to dp of B H minus 1. Yeah, that's correct, and there are no issues with that. The problem is there are two types of bears. Exactly, wounded and healthy. Yeah, you're right, Anton. So this is okay, but with probability B divided by B plus H, we hurt a bear, but we don't know if this bear was wounded already. So we don't know if we go to B or B minus 1. So what is a possible fix? Well, instead of this, we could add one more dimension to count bears with 1 health point and bears with with 2 health points. It's very nice to call them wounded and healthy. Actually, when I invented this problem and when I discussed this with coordinator, I used words like wounded and healthy indeed, but then the number of dimensions is too big. Like the complexity here would be what, n power 4, maybe n cubic after some improvements. Yeah, so this looks like n4, and actually Anton is right that it's n cubic. Why it's not n4, n power 4? Well, the number of dimensions, the number of states is n cubic. but we also have this like every next arrow to consider. But these numbers, the number of wounded healthy bears and humans, it uniquely determines the number of arrows already used. If 5 bears were wounded and 2 humans died, then exactly 7 arrows were used. So for every state we know exactly what number of arrows was used, so we can just from this move to some other state. So yeah, this is solution with this complexity, but we must do better. Okay, what should be an idea for improvement? Well, since we want to like maintain we need probability of hitting someone, and for that we need the number of alive people. And we want to know when someone dies, so when someone has, well, 1 health point. So what we can maintain is the dp of 1, 2, when 1 denotes the number of soldiers with 1 health point, and 2 denotes the number of soldiers with 2 health points. And so here we would start from dp of 2 soldiers with 1 health point and 3 soldiers with 2 health points. And when this bear is hit and it becomes wounded, then we would decrease 2 by 1 and we would increase 1 by 1, because 1 extra soldier would have only 1 health point. And this thing is possible to update, and this solution is n squared. We can compute all of that in n squared, process all t arrows, but there is an issue with that. Well, some words about this implementation is that there is probability 1 divided by 1 plus 2 of hitting someone that has only 1 health point. So we would get to dp of 1 minus 1, 2. And similarly, probability 2 divided by 1 plus 2, that we will like lose 1 of these soldiers, but we would increase 1 by 1. So the alternative is like dp of 1 plus 1 and 2 minus 1. Okay. So this works, but at the end what it gives us is the probability that at the end there is this number of soldiers with 1 health point and this number of soldiers with 2 health points. So for example, it would be okay if we just want the expected number of alive people at the end, or the expected number of healthy bears at the end, because we know the probability that there is some situation, and here we know the number of healthy bears. But here we can distinguish between humans and wounded bears. And this is when our technique comes to life. This is when we use the ordered pairs technique, because what we want to do is for every, let's say that we only want to find the sum over bears times humans. I think this is equally hard as what was given in the statement. I think that this also could be used in the statement, and only this solution would still pass. I'm not sure, I don't remember now. Maybe there is something simpler here. But here, so the product bears times humans is equal to the number of ways to choose a pair, bear and human. And since all bears and all humans are symmetric, we can say that let's focus on first human and first bear. And we want to know the probability that at the end it will be this situation, so we can maintain dp with the number of people with 1 and 2 health points, soldiers, not people. And also we want to know at the same time what is the probability that this fixed person, human person, and fixed bear are alive at the end. And if they are alive, then we add 1 to the answer. So we add this probability that we will get. So what we will actually do is dp of 1, 2, and state of the two fixed soldiers, one human, one bear. So here we have 0 or 1, so whether the fixed human is alive, and here we have 0, 1 or 2, so the number of half points of the fixed bear. And now the same thing, just slightly more complicated, can be done with this dynamic programming that has extra like 6 possible states. And so not only you care whether someone with 2 or 1 half point will be wounded, but also whether it will be this fixed bear or this fixed human. And if yes, then you change this, for example, state from 1 to 0, or here from 2 to 1. And at the end, if here we have that this person is alive, so if this is 1 and this is 1 or 2, so bear is also alive, then you have probability of some situation when this pair is alive, so they add 1 towards the answer. So you can add this computed probability of this situation at the end to the answer. And one thing remains is to, at the end, multiply everything. For example, when you print the answer, multiply it by the initial number of bears times the initial number of humans. Why? Well, because there are this number of pairs, human-bear. We said that bears are symmetric, humans are symmetric, so well, we can focus on first human and first bear. But actually, if, for example, at the end, 2 humans will be alive and 3 bears will be alive. Well, if we computed some probability, let's say probability 10% that he is alive, then the expected number of bears times humans is equal to the number of pairs, ordered pairs, human bear, and the number of pairs, possible pairs, is 6, and each of them has this computed probability. So this is why we compute this, we multiply this by initial b given in the input times h. You can also imagine that you iterate over pairs, so once you do all the computations for first human, first bear, then for first human, second bear, and so on. But since everything is symmetric, all the time you would get the same values. So instead of repeating b times h times the same thing, you just multiply it once by b times h. And you will get the answer. So here you actually had times all in this problem, but first of all, you can add one more dimension for this extra fixed soldier, but it isn't necessary because you know all. All is equal at the end to 1 plus 2. So 1 is the number of alive soldiers with 1 health point, 2 the number of alive soldiers with 2 health points. So 1 plus 2 is equal to all. So actually here we will add this probability to the answer multiplied by b, by h, so the initial value b0, h0 given in the input, and times 1 plus 2. And this is a full solution. So I recommend trying to implement that if you feel confident with the previous easier problems. And if you indeed, without this lecture later, understand this solution, then I think you can say you understand the technique. One more thing about implementing stuff like that. Also, something that I mentioned in the first block, but I didn't cover it, is how to check your answer with a program. It was, for example, here, find the expected value of the number of coin tosses until you get heads. And this is something that, so I will now spend a few minutes implementing something. Can you explain the last part once again? I can. I can explain something once again, and then we'll move to the how to check the answer for such a problem with a program. So to kind of easily, without writing a complicated brute force. Okay, so we said that we can maintain dp of 1, 2. And it isn't enough for us, because at the end we want to know what is the product, the number of bears times the number of humans. For a moment, let's forget about this times all thing. Let's just find the expected value for the product, the number of bears times humans at the end. And from the previous lecture, from the contribution technique, you should know that this product is equal to the number of pairs. Well, it's more from this lecture. The number of pairs human, bear. So just like previously, we iterated over triples or something with for loops. So 1 for, second for. This time we iterate over human and over bear. So this will not be fully visible. So we can iterate over human, then iterate over bear. And here, find the probability that this pair will be alive at the end, and add this probability to the answer. So let's say that we do that. And here, we need this dynamic programming, but with 2 extra dimensions for the state of the fixed human and the state of the fixed bear. And if you think about how to compute this easier dynamic programming, this one is very similar, just slightly more complicated. So you iterate whether you hit this bear, whether you hit this human, or whether you hit some of the soldiers with 2 health points but not this fixed bear, and the fourth last possibility is some of these soldiers with 1 health point, but it can't be either of those. So there are 4 possibilities now. Previously we had like first possibility here and second possibility like here, where we hit some healthy bear. Now we have 4 possibilities, to like each with some probability. And at the end we know, after using all arrows, considering all arrows, we know the probability that this fixed human and bear will be alive. So we know that we should add this to the answer. And we solve this problem with complexity. This dynamic programming is done in n square, but also here we iterate over humans and bears. But actually this part is the same for every pair human-bear. So instead of this for loop, we just compute it once and multiply it by the values computed by h times b, because here we would repeat times this times h times b. And the one last thing is that actually we had multiplied by all. And it's easy to apply because we know value, the number of soldiers with 1 health point, the number of soldiers with 2 health points. So 1 plus 2 is this all. So actually we also like multiply by 1 plus 2. And then that's it. Okay, so this one last thing. How to check your answer with a program. So let's say, so I will focus on an easier problem. Let's say that we computed, so here there was some discussion in comments about this problem, so I will do something that is like useful for them as well. There was a harder problem the expected number of tosses until you get 2 heads in a row. So let's implement this process. So we toss a coin each time, and at the moment when we get 2 heads in a row, we stop. And what is the expected number of tosses? Let's implement this process once. So int previous result is -1, let's say, and int tosses is 0, while true, infinite loop. What? Round modulo 2 is then like new result. Now we increase the number of tosses by 1, and if previous result is 1, let's say that this denotes heads, and x is also 1, then we return the number of tosses, and if not, we continue. And here previous result is x. So here is just implementation that tries this process and returns the number of tosses. And here let's try that 1000 times, for example. Let's make a constant for that. So repeat this number of times. Find the sum. Well, let's use for that double, because we'll do some average value. Let's find the average number of tosses we need. And here we print sum divided by the number of tries. So this is average value. And run. And what it printed is 6.03. Of course, it isn't exact, because if you, for example, toss a coin 10 times, then on average it will be 5 heads. And also if you toss 1000 times, on average it will be 500 heads. But it will be slightly different than that usually. In fact, you should expect that if you make n tries, then your n tries means precision 1 divided by a square root of n. This is some probability theorem. For example, if you try 10 power 6 times, then precision will be 1 divided by square root of that. So it will be this precise, like up to a constant. So let's here try 1,000,000 times. And here I expect much exact result, like with this precision, times some small constant. But of course it's a bit slower, but still. And yeah, now we got 6.004. So it's this error. So I think now that the exact result is 6, and it's just an error. We can try like a bit more, and now I think it should be even closer to 6. And now we got some much better estimation. Of course, it can oscillate, like it can fluctuate, it can be a bit smaller. Also, it would be possible that here we would get something less precise than here. Just, yeah, here, for example, we got slightly smaller value than 6. But yeah, we see that it's around 6. And someone in the comments asked, I think, asked whether it's this value. So after solving this, we can get r equal to 6. Is this correct? So yeah, I can answer yes, it is. And this is how you calculate that. And while here it was a quite easy example, so it wasn't hard to code it, but with this you can check your calculations. So here Janish used the technique that was showed in the previous block, more or less, and he got this result. And with this, like trying many times, you can check if your result is correct. And I'm saying that because you could also use it in our problem today. For example, if you have this double life problem about the birds and humans, and here actually in the problem it was said to print some number modulo billion plus 7, but it's easier to implement that for doubles, for real values. And like I recommend trying that instead of fighting with modulos. And then if you get some result for some input, you can check that with a program like this. So here we could get the number of birds, humans, and the number of arrows, and like every time hit a random person, and at the end just return birds times humans times all, and take an average of that among like 1 million tries. And this way you test your program quite easily without writing a separate brute force. It's just, this is a very easy thing to do. And I know it as so I know this as a term Monte Carlo method. I'm not sure if this is correct term, but this is what I use myself. Okay, we solved all the problems. If you want more, take something from comments from this block or the previous one. And this is the end of the 2 parts lecture. I hope you learned something. And if you first thing, if you don't feel confident about some part, just later watch this part again. If what is very important in practicing a new topic is actually trying to implement something. So, for example, try to write this square of wins problem, for example. First, maybe try without looking back at the lecture, try to implement it. Then, writing something like this Monte Carlo method, estimate whether you are correct. So, if your result for some input will be 5.5, and this Monte Carlo will say you 5.4999, then it means you're okay. So this is how you can yourself, without submitting anywhere, you can check the correctness of your program. Just try a few inputs. So try to do the calculations needed for this problem to make sure that you can solve it. And if you want a more complicated problem, then the same, but for third powers. I don't recommend fourth powers, and then it's like, it isn't pleasant. And think whether you understand the remaining problems. And if you do, this problem is quite nice to implement once you understand everything. So it isn't very long. And I want to thank you for watching. It was nice streaming to you, answering questions. So as I said, I see you back on the next stream in like 2-3 weeks after my USA trips. You can cheer for me in Facebook Hacker Cup and Top Coder Open contests. So the information about them will be, I guess, on Codeforces. Also, go check my Facebook page. I will post some updates there. And I will try to make some shorter videos while I'm in travel. About some, I guess, easier problems, not necessarily a lecture like this. I will not have time for that because I will be traveling. Yeah, and if you have questions, just write to me on Facebook or Discord. So, yeah, thanks, William, for watching. Thank you, everybody, for watching. And bye-bye. Thanks, Larry, a lot. Yeah. I'm glad you liked the lecture. Bye, everybody.